Okay, thank you very much for this invitation. It's actually a pity I cannot be there. So I'll give a focus talk also because Emanuele gave a great introduction to the topic. And actually, I will focus on the second part, so the argument that goes under the name of exotic compact objects. But actually with a different twist. So I'll try to discuss these new solutions that have been found in basically string theory and supergravity that have the hope to describe the microstates of black holes, and the goal would be to understand their signatures. So this is based on two recent papers done with these people here, in particular Pierre Heitman and other collaborators. Very briefly on the motivation, as Emanuele was saying, we have a lot of modified theory of gravity. Sometimes it is arguable whether they should actually have corrections that we can observe in astrophysics, just because the scales we are testing in astrophysics are very different from those in which modified gravity should actually occur. So it's important actually to find instead models that have very strong motivations. And in fact, when we talk about black hole physics, there are strong motivations to test black holes, and probably they are listed here, the main one. So the main one is that black holes have a huge entropy. For example, for M87, the black hole seen by the Event Horizon Telescope, the entropy corresponds to this huge number of states. And this is at really clash with the prediction of general relativity that black holes are essentially elementary particles. So they are described just by the mass, spin, and angular moment, and the electric charge. This huge entropy is actually related with the information loss paradox, so the fact that black hole evaporation violates unitarity. And finally, we know that black holes have singularity in their interior, where Eisen theory breaks down. So these are big theoretical problems that we would like to eventually resolve. And there is a program, typically called Fastball program or black hole microstates, that aims at solving all these issues with regular horizonless microstates. And the idea is that black holes as classical solutions to GR are just a thermodynamical description of something more fundamental, which are solutions that you may interpret as solitons in string theory. So asymptotically, these solutions are just like black holes with the same mass and spin, potentially, but eventually down to the high redshift region, they terminate with a regular geometry without an horizon and without a singularity. So this is very appealing. However, in string theory, many microstates have been found, but only mostly for extremal solutions, supersymmetric ones, or non-spinning. So actually not very realistic. So the goal is to try to build microstates for astrophysical black holes, which are probably neutral and of course rotating, and eventually confront them with the data. So when you try to do so, there are a few big issues that you would like to resolve. In particular, try to mimic black holes as much as possible. So we know that black holes are dark, for sure, so you need a dark object. You need the object to be very compact, and this is actually hard to do with ordinary matter. And probably most importantly, for a black hole, the mass is a free parameter of the solution, and this is related with what Emanuele was saying. For a boson star, it's impossible to describe all black hole in the universe just because the boson star has a mass scale that is fixed by the parameter of the theory. So you need solutions in which the mass is free, and also the size of the object grows with the gravitational interaction, which is also very counterintuitive because in any theory we know of, the stronger the gravitational interaction, the smaller is the object actually for a fixed mass. And of course, you want them to be stable at least over astrophysical timescales and also mimic all peculiar properties of black holes in terms of multiple moments, tidal deformability, quasi-normal motoring down, as Emanuele said, etc. So matching all these requirements is nearly impossible within GR and ordinary matter, while it is possible in the fastball approach. And the main ingredient is that, well, you have a well-defined theory, a top-down theory, that is intrinsically higher dimensional. It comes with very peculiar topologies of string theory, and these properties are crucial actually to have all these requirements to mimic a black hole. And also it comes with the fact that when you actually look at this theory in 4 dimensions, it has very unusual pathological properties that can evade, for example, the no-hair theorem that we are familiar with. So it's a very promising approach, and the goal is, well, find solutions to this theory and test it with observations. And well, I will be very brief here with the fact that, as Emmanuel already was saying, that there are interesting effects to look both in the spiral, in the ring down, in the merger, that we would like to use to test these ideas. So I will skip all details about these, how these solutions were obtained. Let me just mention that they are solutions to this theory here. These are very well motivated theory. It's 5-dimensional minimal supergravity. And the idea is that we will look at this theory in 5 dimensions, but there will be an extra compact dimension. So we will eventually compactify it because we know that we live in 4 dimensions. So the extra dimension will be very small. This theory admits an analytical solution that is regular and smooth, so no horizon, no singularity, is written here in terms of 2 parameters, the mass and the charge. You can set the charge to 0, as I will mention later. And the important point is that when you compactify this in 4 dimensions, it takes this form here, and the solution appears to be singular. So there is a curvature singularity in 4 dimensions, which nevertheless is harmless because the 5-dimensional embedding is completely regular. So this also tells you that you have to be very careful with singularities in 4D if you have a well-defined theory in higher dimensions. So an interesting property of this solution, well, is first that it has the same mass and charge of the corresponding black hole. So it really describes a microstate of this solution, of this black hole, without any horizon or singularity. And there are no tunable parameters. So there is no small parameter that you can at most hope to have an upper bound for. Here is really a model that can be falsifiable in the sense that it will make concrete predictions. And well, if you go there, measure the properties, and eventually they do not match with the prediction of the theory, you can rule out the model completely. The mass of this solution is a free parameter, precisely as I was mentioning before, and the neutral solution is particularly simple. This is the microstate of a Schwarzschild black hole. It has the very same redshift factor, and it comes with an extra field coupled to gravity. So notice that these coordinates are actually the non-spherical ones, so the effective size is given by this combination here, and is proportional to the size of the extra dimension. It can be parametrically larger, but is dictated by this number here. The solution is spherically symmetric, so the geodesic motion and perturbations are separable. And let me just mention that it has a light ring, just like black holes. So here you see the comparison between the soliton and the black hole. Here it's called black string because it's in 5 dimensions. You see that both the light ring, the shadow sides, the Lyapunov exponents of these geodesics, the angular velocity, they are all qualitatively similar to black holes, but yet there are differences at the level of 10%. And again, there is no tunable parameter. So this is the prediction. You cannot actually make it closer to the black hole. And this is why actually you see when you compute geodesic motion, for example, the shadows of how these objects look like in the sky, if you compare, for example, here, how an accretion disk look like in a black hole case and in the corresponding microstates, you see that they are very, very similar, except for small deviations that, well, you need a lot of resolution in order to distinguish. So this is just to mention, you can also test these objects with electromagnetic probes, but I will now focus on the gravitational wave signature. So the very first thing you want to know is to study the ring down, as Emmanuel also was discussing. And let's start with scalar perturbations, the simplest one. These perturbations can be decomposed and separate in an angular part in a radial equation, which is different for the soliton and for the black hole. And the angular perturbation is particularly interesting because it corresponds to spin-weighted spherical harmonics with half integer spin, which comes with a particular angular eigenvalue quantization. And well, let me just mention something not related, but by studying this problem, we realized that actually it was important to impose this angular quantization for spin half integer perturbations. And this actually prompted us with Sumanta, Chakraborty, and Pierre to study fermionic perturbations of black holes in GR. And we found recently in this paper that their log numbers under fermionic perturbation is non-zero. So while for the bosonic sector, the response of a black hole is purely imaginary, for the fermionic sector is actually purely real and non-zero, even for Schwarzschild. And this was a nice byproduct of the analysis that has nothing to do with microstates, but I thought it was an interesting result. So when it comes to scalar perturbations, so you can compute them with whatever methods, and what you find is that the deviation with respect to the black hole are small, but still sizable at the level of 10%. The potential for a soliton is positive, which means that it's completely stable under scalar perturbations. And then you may actually go and look for whether you can constrain these deviations with data. And taking these outstanding events that was also discussed before, you see that at the moment, the accuracy of the first overtone frequency is about 30%. The deviation in this model is about 10%, which means that it's still within the observation so far, at least for what concerns the ring-down only part, but a slight increase of the accuracy might rule out the model completely, because if you reach the level of 10%, you will be able to distinguish these deviations completely. You can also study the model in time domain, and well, you get what you would expect. So there is a standard ring down. The ring down can be associated, can be described as a superposition of the quasi-normal modes of the system. And interesting enough, connected with what was discussed before, this model can mimic black holes very closely, but they do not have a stable light ring. And this is why actually there are no echoes in the light time in the late time ring down signal. So in a sense, they are closer to a black hole because they have just a ring down, but on the other hand, they are not compact enough. So you see these deviations from the standard ring down that might be bigger or smaller depending on the angular momentum of the perturbations. Very recently, we also extended with Pierre and George Santos these microstates to the rotating case, which is actually very challenging from the technical point of view. Let me just mention that there are analytical solutions described by 4 parameters. The angular momentum and the mass are both quantized, consistent with the fact that these are really the fundamental microstates of your solution. Interesting enough, these solutions do not have a 4D ergo region, but they have actually a 5-dimensional ergo region, which points to the fact that when you look at the 4D compactification, they should not have any ergo region instability, but modes with dynamics in the 5th dimension might actually have display an ergo, they see the ergo region and might display an ergo region instability, which is an instability that occurs anytime you have ergo region without an horizon, because also these solutions are completely regular. Again, the geodesics and the scalar perturbations are separable in this case. And let me just close by mentioning something else, that you can study the quadruple moments of these solutions that will be important in the in-spiral, not in the ring down. And an interesting property of this solution is that at variance with black holes, the quadruple moment can be either negative or positive. So a negative quadruple moment means that the object is oblate, as you would expect, so it develops a pancake-like shape when rotating. A positive quadruple moment means that is Seeger-like, and this is very hard to obtain with ordinary matter, just because ordinary matter, when you spin it, it tends to acquire an oblate shape like precisely a Kerr black hole. Well, it's interesting enough that data so far do not exclude one possibility or the other, just because the error bars on the quadruple moment are so large that they are still consistent with Kerr, but actually they sort of tend to prevent positive quadruple moments rather than negative. And again, it's very exotic having these positive quadruple moments, but it will be very important in the future. So we are looking forward future tests to check whether these differences remains or the value predicted by Kerr black holes is actually more compatible with the data. So I think it would be interesting to test this in the future with more accurate data. So I will conclude just by saying there are these new solutions. They are analytical. Many things can be done with that. There is a sort of short blanket problem in the sense that there is no tunable parameter. So there are deviations from black holes. They are sizable and measurable, which is actually very good from my perspective because it means that the model can be ruled out. It's not only that you will put upper bounds and is a handless job. So we are looking ahead for more follow-up work on this, in particular studying gravitational perturbations, their stability, studying more in details quadruple moments, the law of numbers, develop waveforms for the spiral and ring down these solutions, possibly also doing simulations for the merger. And I think that the holy grail of all of this would be finding neutral and rotating solitons that would describe the microstates of a Kerr black hole, and that really would be the final comparison between this model and black holes. So I will stop here and I'm happy to take questions.
Thanks, Paolo, for this nice talk. So we have time for a couple of questions.
So hi, Paolo. So as of now, we have very high SNR signals, which are quite long and all that. So in those clean signals, do they still support this kind of exotic systems?
So
by the in-spiral phase itself?
Yeah, I mean, this as you can see, is taken from the test of GR paper with the third catalog. And the problem is that measuring accurately higher post-Newtonian corrections is very hard. Also, Emanuele showed a plot, the violin plot with the deviations, parameterized deviations for the post-Newtonian parameters. The 2pm deviation, which is the one important for the quadruple moment, is pretty large, as you can see here. So this parameter is essentially the deviations from the Kerr moment. So it's normalized such that Kerr is 0, but a deviation of 100% from Kerr, which is pretty large, will correspond to delta K equal to unity. And as you can see here, the width of this posterior is actually of the order 10 or even more. So the error bars are still very, very large here. I'm sure that with the new data that well, also people in the audience are analyzing, these error bars will shrink, so it will be more and more difficult to accommodate deviations. But I would say that at least in the spiral at this moment, there is still room for even large deviations.
Thanks.
Any other?
Hi, Paolo. For this exotic model, do you know any? For any of these stars, do you know any dynamical formation channels, or these are just completely phenomenological model?
No, these are actually really top-down models in the sense that you can take, well, this theory here, and in a sense, you can think of these solutions as boson stars on steroids, let's say, in the sense that they have very nice properties like black holes, but they have a concrete theory. So if you collapse these fields in this theory, you should form these solutions. We are actually working on this. It's challenging from the technical point of view because the solutions are complicated, but it's a concrete model. So they should form like boson stars form. A different challenge would be if you take two of these solutions, when they, for example, merge, would they always form a black hole or they would form another of these solutions? I think that both possibilities will be possible, at least within classical theory, and it would be important to understand the parameter space in both cases.
Any other questions, comments?
So what is the interpretation of this Q?
So this Yeah, so in this particular solution, Q is the electric and magnetic charge, because these solutions have several charges. And in order to write it in one line, I choose the simplest solution in which all the electric and magnetic charges are the same and they are equal to Q. So this is really the charge of these fields. So in 4D, you have you have a gauge field and also some scalar fields. So from the 4D perspective, this theory is a very particular version of Einstein theory coupled with gauge field and scalar fields. So a sort of Einstein scalar Maxwell theory. So Q is basically the charge of the Maxwell field. You can set it to 0, so have a neutral solution, or you can keep it. Clearly, if you keep it, it will have other consequences. So there might be electromagnetic radiation, for example, in the spiral. So you might actually, want to neglect it from astrophysical purposes, but the solution is general. So this is a sort of generalization of Rayleigh-Nostrum black hole, if you wish.
So if there are no more questions, let's thank Paolo again for this nice
Thank
talk.
you.
And Paolo will have our discussion session maybe 1 hour 30 minutes from now, if it is possible, for you to join.
Yeah, I'll try it. I don't know how long it is because I'm now running to lectures. I will be done essentially in like about 1 hour and 45 minutes, and I will connect immediately after. So if the discussion is still going, I'll be happy to join.
Yeah. Okay. Sure. Thanks.
Thank you. Bye-bye.